Hello, myself, Dr. Ajay Sharma, Department of Electronics and Communication Engineering, James Engineering Management Technical Campus, Greater Noida. The subject that I teach in this particular semester is digital communication, and the topic that I will discuss today is companding. Okay, to understand this companding process, first we have to focus on why we do companding, right? Actually, when you do quantization, uh, you take the samples, right? Some samples have a high value, some samples have a low value in the sense of voltage. Means some samples have high voltage levels, some samples have low voltage levels. So if high voltage level, if you consider high voltage level, say for example 12.6, so this 12.6 is approximated as 13, right? But when you have a low voltage level sample, say 1.6, it approximated as 2 volt. So, the percentage of error is more in low voltage levels as compared to high voltage level, because 12.6 is approximated as 13, so it's a difference of 0.4 volt, and 1.6 approximated is 2 volt. Again, we have a 0.4 volt difference, but that difference is more in the case of 1.6 volt rather than 12.6 volt. Okay, so that is that is to be the low voltages have high percentage of error, quantization error, as compared to low voltage levels have high percentage of quantization error as compared to high level of voltage levels, right? So to minimize that difference, what we have to do, we have to do companding process. Actually, companding process have have two processes involved in this companding process. One process is compression, and another process is expanding. Then if you do compression and expanding, then you do companding, right? So companding means you do two processes. One process is compression. That process is to be done at the transmitting side, and another process which we call as the expanding. This is to be done at the receiver side, and the whole process which we call as a companding, right? And what is the benefits of companding? It's the main benefit of companding is that the companding keeps the bit rate and bandwidth low. This is one of the, or not only that, there is there is a uniformity should be maintained by doing this companding process. Means all the voltage levels have same amount of percentage of error, right? So what we do, we artificially boost, you know, boost some samples levels which are low, and that voltage level that are too high is to be shorter. So in this way, all the voltage levels are at the same level, right? So the percentage error involved is also the same, right? This is all about companding. So as I discussed earlier, the word companding is the combination of compression and expanding. Compression is the process that is to be done at the transmitter side. Expanding is the process that is to be done at the receiving side, which means that it does both. So companding means both process, compressing and expanding. And this is a non-linear technique which is used in pulse code modulation, which compresses the data at the transmitter and expand the same data at the receiver. So what we do in compression, we have to compress compress the data at the transmitter side and expand the same data at the receiver side. Remember what the ratio of compression at the transmitter is same as the ratio of expansion at the receiver. So overall, the process, sorry, So the effect of noise and crosstalk are reduced by using this technique. So as I said earlier, compender is nothing but it's a combination of compressor and expander. Compressor is a component that do compression. The expander is a device that do expansion at the receiver. So compender is a combination of compressor and expander. So in non-uniform quantization, the step size varies. So what we have to do, we have to vary the step size, right? So this is the form of non-uniform quantization. In non-uniform quantization, the step size varies. The use of non-uniform quantizer is equivalent to passing the baseband signal through a compressor and then applying the compressed signal to a uniform quantizer. The resultant signal is then transmitted. So first we do compressor. After compression is done by compressor at the transmitter side, and after the compression, we have a uniform quantizer. Then the expansion process at the receiver, that is to be done by expander. Right? So in this particular picture, we have to see that there is a model of non-uniform quantizer, right? So indirectly, non-uniform quantizer is actually uniform quantizer, right? So at the receiver, a device with a characteristic complementary to the compression called expander is used to restore the signal samples. Actually, the working of expander is reverse at the as compared with the compressor, right? So compressor, expander are work oppositely. Compressor compress the things and expander expand the thing in the same ratio. So the overall process remains the same, right? So expander is used to restore the signal samples to their correct relative level. So the compressor and expander takes together constitute a compender. I again say compender is the combination of compressor and expander. Compressor is done compression at the transmitter side. Expander done expansion is done by expander at the receiver side, and both compressor and expander combine together to form a compender. So compender is a device having two devices, compressor and expander. Is it clear? So we have two types of companding. One companding that we talking about A-law companding technique. Look at the A-law companding technique. This is the input and we have the output. So look at this particular picture. As I said, these are the non-linear type of devices. So show non-linearity. So when A is equals to 1, it is a linear. It's a linear. So uniform quantization is achieved at A is equals to 1. So A is to 1 shows a linear, and linear shows a uniform quantization, right? So for uniform quantization, we always have a curve which is a straight line. So at A is equals to 1, we have a straight line, and this is the case of uniform quantization. And all the curves that we have shows a non-linearity, and that all the curves come in the category of non-uniform quantization, right? So A law has mid-rise at the origin, hence it contains a non-zero value. A law of companding is used for PCM telephone system. So this type of A law companding is used in pulse code modulation telephone system. This is the picture that shows A law characteristics, right? So we have different values of A, accordingly different curves. So A is equals to 1 show a uniform quantization, and other curves show a non-uniform quantization because all are non-linear. And non-linearity means non-uniform quantization. And linear means uniform quantization. Okay. Now another technique is micro law companding. So uniform in this particular picture, uniform quantization is achieved at mu is equals to 0, right? At mu is equals to 0, again we have a straight line, and this is the form of uniform quantization. And other curve shows a non-uniform quantization, right? So micro law has mid-treat at the origin, hence it contains a 0 value. Micro law companding is used for speech and music signals, right? So that companding is come in the picture when you have to deal with a speech or music signal. So we have to use that companding which we called as a micro law companding, right? And that micro law companding normally used in North America and Japan. Thank you very much.